on homework questions. Because you have 7 questions, it's kind of hard for this week's homework. So just start answering any questions about homework.
Hi, I had one question about number 4, how to just get started in general.
Yep. Right. How about this time? Let's do it in order. Like if you have like a question, like for question 1, question 2, question 3, like just in this case, I mean, students who watch recordings, they can easily find the questions that they're struggling about. So I just do, like if anybody have any question about homework 1 or like question 1 or question 2 on independence, if yes, you just yell it loud and first talk about like questions independence and then essential limit theorem and then conditional probability.
Yeah, I actually had a question about number 2.
Yep.
Yes.
Yeah, I'm just wondering how to approach it because I had like an answer in mind, but then it said to be careful. So I'm wondering what that's referring to.
I think this question, like you cannot do it by computation, right? Because you don't have any kind of number. So unlike question 1, where you can really calculate the probability of, for example, A intersect B and to see if that equals to the probability of A times the probability of B, right? If that equals, then you have the conclusion of independent. If it's not equal, then it's not independent. But question 2, like you cannot do such kind of numerical calculation. So it's really about like the definition of independence, like what is the meaning of if 2 events are independent. And here, like the 3 decisions are independent, it's just equals to if any 2 decisions are independent. And it's more like a definition based question, like what's the meaning of independent?
Okay, thank you.
Victor, I had a question about number 1.
Yep.
So like it's hypergeometric, so like I understand like in this case it's dependent, but I was just wondering if like generally hypergeometric is always like the events are dependent.
Yeah, it's true. Like for this case, like intuitively, we know, let's take an example, like what's the probability, let's say, of getting an ace in the second term, right? So basically, it's very hard to calculate this one because you have to know what's the outcome of the first turn. Like when you take the first card out of the deck, if that card happens to be an ace, then the probability of getting a second ace in the second turn is kind of decreased because there's only 3 aces in the deck in the second turn, right? But if during the first turn, like you take out some other cards, then in second term, the probability of getting ace is just 4 divided by 53 because you just take out 1 card. And here you know, right, the probability of getting a particular card in the second turn is related to the result of the first turn. So it's independent. So it's not independent, it's actually dependent with each other. So that's that's an intuition of how this question is formed, and I guess that's just your thought about it. But in general, so to answer your question, yes, in hypergeometric distribution is not independent. But to solve this question, I really want you guys to do some calculation, to do some computation, right? The most clear way to argue that two things are not independent, let's say two things, event A and event B. To argue that event A and event B are not independent, you need to have such inequality that the probability of A intersect B is not equal to the probability of A times the probability of B. If that inequality holds, then you have the dependent variable to each other. If you change that inequality mark to an equal mark, then that's the independent, right? So basically you can just do some kind of like a simulation. For example, I say event A is getting an A in the first peak, and event B is again getting an A but in the second peak. So what is the probability of A intersect B? It's just you just get two A's from the two peaks, and you can calculate that. It's just like a binomial distribution. It's just a hypergeometric distribution, where in the denominator is 54, I think 54 choose 2, and in the numerator is just 4 choose 2, because you only have 4 A's in total. And that's the probability of A intersect B. And then you just calculate what's the probability of A getting an A during the first peak. That is 4 divided by 54. And what's the probability of B getting an A in the second term? It's more complicated. You cannot just derive a number in 1 second, because it depends if the first term is an A or not, right? So you kind of need to calculate the probability of B, the probability of getting an A in the second term, and you just split it up into two scenarios. What if the first term happens to be an A, and what if the first term is some other cards? And you just add those two probabilities together, and you can get the probability of getting an A in the second term. And you multiply probability A times probability B, and to see if that equals to the probability of A intersect B. And like eventually you get an inequality.
I'm confused because I used the P of A given B like formula independence, and I got that they were equal to each other.
True,
That-
but you cannot use A given B. Like for independence, it's always if the probability of A intersect B equals the probability of A times the probability of B. Like that given mark, what does that given mark mean? That given mark is something close to dependent. The probability of A given B. So first B happens, then the probability of A happens, right? So kind of that given mark gives you a hint that A and B are dependent to each other. So don't use given in like to compute if two events are independent. The only way to argue if two things like are independent is probability of A intersect B. In other words, probability of A and B happening together, is that equals to the separately the probability of A alone times the probability of B alone.
But so the probability of A alone was 4/52, because like we could represent it as being like It's 4. Like, let's say we like assign a number. Let's say we want to pick a 3, right, out of the deck. So
Yeah.
there's a 4. There's 4 3s, and there's 52 cards. So that means the probability of A is 4 of 52. And for B, we're trying for probability of B is like the color, like we're picking from that number, we're trying to pick a red. And we can do and that's basically, isn't that like 1/2? Because there's 2 of that, like 2 reds of that number, or no? Is that wrong?
I guess you're gonna like assume B is also like picking a particular number. And in my example, I just used two same number for the first pick and the second pick. I guess it's more computational easy. So how about let's do this? Like so this question, if the two events are independent, the question 1, it's just equals to, first you calculate the probability of getting 2 A's in a row. Right, and it's very easy to calculate, just a hypergeometric distribution. And then you find the probability of getting an A in the first term. And if, like you said, if there's only like 1 to king, like A's to kings, like 13 cards, each with 4, you have 52 cards in total. I use 54, but like it's similar, like it doesn't influence the answer at all. So you use either 52 cards or 54 cards. What's the probability of getting an A in the first turn? And then you compute what's the probability of getting an A in the second turn. You multiply that and to see if that equals to getting 2 A's in a row.
Victor, for that one, can you not just also say, like, after you deal the first card, there's only 51 cards left, so that changes the probability of getting, like, the same, like, for example, the same ace twice, or same ace in the second turn? Because wouldn't that change the probability?
Yes, but you have to find out what's that probability. Yes, that probability is changed. Like it's dependent on if the first one is an A or not. But let's assume you don't know the outcome of the first one. You still can calculate the probability of the second one. Right? It's just like 4 over 52 is the probability of getting an A in the first term. And you use that 4 over 52 times 3 over 51. Like the formula is 4 over 52 times 3 over 51. That's the probability of getting an A in the second term, given during my first term I get an A. Right? But you have to add this probability with another subset, which is the probability of getting an A in the second term, given I didn't get an A in the first term. So you have to add that two subset together, and you can get your probability of finding an A in the second term alone.
Can we go over number 3, please? Because I'm pretty sure we have to use the central limit theorem. I'm just not sure how to like approach the problem from the start.
Number three is also like independent, right? So basically for number 3, like you don't use the central limit theorem, I think. It's also like a question on independence or not. So you're gonna use the like exactly the same argument. If the failure of type 1 and type 2 being independent, you just calculate the probability of type 1 and then the probability of type 2. It's easy to do it. It's much more easier than question 1. And then you multiply them together and to see if that equals the probability of type 1 and type 2 happens together, which in statistical term, the probability of type 1 intersect type 2. In this case, it's 15. So basically, first you calculate what's the probability of type 1 failure, and then what's the probability of type 2 failure. And the probability of type 1 and type 2 failure is just 15 divided by 1000, right? It's very easy to calculate, and you just multiply that two independent probability together and see if that equation holds. Like if that equation, doesn't perfectly holds, but almost it's the same, then that gives you enough evidence to argue the failure of type 1 and type 2 are independent.
Okay, I understand. Thank you.
Is there a specific range that's like close enough? Because when I did it, I like mine was different by 0.003. I said that's relatively like the same thing. Is that fine?
I think it is.
Okay, thank you.
Just make sure, like the probability of a type 1 failure, like you don't use 131 divided by 1000, but you should use 131 plus 15 divided by 1000.
Oh.
Right.
Oh, okay, yeah, that makes sense. And then same thing for the other one, it would be the whatever 89 plus 15 over 1000.
Yes, because the probability of type 1 failure includes both the probability of type 1 alone and the probability of type 1 and type 2 together.
Okay, that makes sense. Thank you.
Yeah.
So we're plugging our values in for the independence formula for the P A given B this time?
For the independence, for the checking of independence, you always use A intersect B.
Victor, so you said that we have to use 89 plus 15 instead of just 89?
Yeah, it's true. Because think about it, what's the probability of a type 1 failure? You just need to answer this single question. What's the probability of type 1 failure? What's the frequency? It's 89 times 15, right? There's 104 instead of 89 times that I encounter a type 1 failure. Right? Does that make sense?
Yep, thank you.
So yeah, you just think about what's the probability, and to compute what's the probability, you're gonna first compute the frequency, and what's the frequency means how many times do I encounter a type 1 failure, right? There's 89 times when I encounter a type 1 failure again alone. However, there's still 15 times where I encounter both type 1 and type 2 failing. So I need to add those two frequencies together.
And so if those two frequencies are not equal to the probability of A given B, then it's not
A given B, A intersect B, meaning A and B together.
I see. Okay.
So
all right,
it's
thank
15.
you.
Yeah, A intersect B, the frequency is 15, and the probability is 15 divided by 1000.
how did you find the frequency for type 1 and type 2?
It's given in the question.
Oh, those are okay. Thank you.
Yeah. And some people just ask for question 4, so I do question 4. Here you need to use the central limit theorem. So first I just tell you like if you sum up 10 uniform distribution together, then the summed up distribution you can approximate as a normal distribution. So you're gonna use the central limit theorem. You're gonna compute your z statistics or z score. I think like last week's or like the week before, you did a problem on like 20 coins. Like you chose 20 coins and what's the probability of getting 9 heads, 10 heads, and 11 heads. The way you do it, sometimes you use the formula of binomial distribution, but still you can use the central limit theorem to approximate the binomial distribution as a normal distribution, and to find your z score or z statistics, and the same approach happens here. But using the z score or z statistics, some parameters you need to know. First is the mean, right? So remember how to find the z score. Is your, I guess it's the formula is something like your mu, your mean, minus what you want to find out, and in this case it's 7. The mu minus 7 divided by standard deviation, and that's your z score. And having this statistics, you can compare that in a z table and you can get the probability. So here, first you need to know what is mu, and second you need to know what is the standard deviation. So mean and standard deviation. And what you now know is for a uniform distribution, a single uniform distribution ranged from 0 to 1, which means like in the interval 0 to 1, like the probability of getting any number in this interval is equal. So the mean is 0.5 for each uniform distribution. The mean is 0.5. The standard deviation, I think you should cover that in class, but if not, I just tell you it's a minus b squared divided by 12. That's the variance, not the standard deviation. I think that's the variance, but you can check. I think that's the variance of uniform distribution, where a here equals 1 and b equals 0. So just find the distance of the interval, which is 1 minus 0 equals 1, and you square it. In this case, 1 squared is also 1, and then you divide it by 12. That's the variance. So now you have the mean and standard deviation, or let's say variance first. You have the mean and variance of a uniform distribution, but now you are adding 10 identical uniformly distribution together, and that forms a new distribution, which I already said you can approximate it. You can approximate as a normal distribution. But what's the mu and standard deviation? What's mu and variance? The mu is pretty simple. It's just 0.5 times 10. You have 10 uniform distribution. You add them up, and the new distribution just have a mean of 10 times 0.5. The variance is more complicated. So basically, you know the variance of a plus b, like a and b are just some random variable, right? The variance of A plus B equals to the variance of A plus the variance of B plus the covariance of A and B. You should kind of know this formula. I don't know if in class you covered this one, but it's very important. And when you take, I guess when you take foundation in finance, when you take some economics class, you will use this formula again and again and again. So it says the variance of A plus B, the sum of A plus B, the variance is not simply the variance of A plus the variance of B, but you have to add another term, the covariance between A and B. And similarly, the variance of A minus B is also like the variance of A plus the variance of B, and then minus the covariance of A and B. So you have another term which is a co-movement, the covariance between the two random variable. But in this case, since the 10 uniform distribution, they're independent, right? You have 10 independent random variables. And that means the covariance between each two are just zero. They don't have any covariance. Like the movement of one random variable can't give you any hint on the movement of all other 9 variables because they're independent, which means they don't have any covariance. Covariance is just a measure of co-movements. So in this case, the variance of A, B, C, D, like you have 10 random variables, the variance of the sum of all those uniform distribution is just the variance of A plus the variance of B plus the variance of C, etc. So it's 1 over 12 plus 1 over 12 plus 1 over 12. Again, you plus it 10 times and you get a 10 over 12. That's the variance of the whole distribution. And the standard deviation, you just need to take a square root. So basically now you have your expected value, your mu, and your standard deviation. I think it's the sigma. You have the mu, you have your sigma, and you can use them to calculate the z-score. Your z-score is just mu minus 7 divided by sigma. That's your z. And you compare that to the z table.
Victor, so when you were talking about covariance only exists when the events are dependent on one another?
Yes.
Okay.
And that's like in reality, that happens majority of time. Like when you take a finance class, right? The stock price, I would say like the commodity price of like gold is very dependent on the commodity price of silver. Like those two prices, they kind of co-move together. When gold becomes more expensive, it's very likely that silver becomes more expensive. So in real life, you have a lot of co-movement or covariance between two random variables. But here, right, you're just given 10 independent random variables. So that's lucky. You don't have to worry about the covariance term. Just add different variants together and you get your final variance for the whole distribution.
Can we go over number 5?
Right, it's very similar to question 4, right? So you're gonna use the central limit theorem, and basically x minus y also follows a normal distribution because you just plus or minus 2 normal distribution together and you get a normal distribution again. right? Well, why you have plus or minus 2 normal distribution? Because central limit theorem, right? You have 1,000 toasting, right? Initially, it's a binomial distribution, like toasting a coin. You have two outcomes, each with probability 0.5. That is a standardized binomial distribution. But since you're toasting them 1,000 times, that converges to a normal distribution. So the random variable x and random variable y, they all follows a normal distribution approximately. And then you have x minus y. It's pretty similar to question 4. X minus y also follows a normal distribution. And again, you're going to use the z-score. So first you're going to calculate what's the mu of x minus y and what is the standard deviation of x minus y. And you can plug in those two statistics into the z-score formula. And it's very easy to, again, it's very easy to know the mu. For many times, mu is like easier to calculate than standard deviation, than lambda, than sigma, because the expected value of a plus b, again, a and b are two random variable, and the expected number of a and a plus b always equals to the expected number of a plus the expected number of b. And if I change the notation to minus, the expected number of a minus b always equals to expected number of a minus the expected number of b. And unlike variance, like you remember the variance I just went over in question 4. The variance of a plus b is the variance of a plus the variance of b, and then plus the covariance of a and b. But this problem doesn't exist in the expected value. Like no matter if a and b are independent, no matter if they have co-movements or not, the expected number of a plus b always equals to the expected number of a plus the expected number of b. And here it's easy to see the expected value of x is 500, right? It toasting, like x be the number of heads in 1,000 toasting. Like what's your expected heads? 500. The expected number of y is also 500. So the expected value, or the mu, of x minus y is just 500 minus 500 is 0. And like it kind of aligns with our intuition, like you have two, like you toasting coins, x be the first toast and y be the second, and the expected value of the x minus y is just 0. But the variance, and then we're gonna calculate the variance of x minus y, which I already gave you the formula, is the variance of x plus the variance of x plus the variance of y, and then minus the covariance of x and y. And here again it's independent. This two, like the result of your first 1,000 toasting doesn't impact the result of your second 1,000 toasting. So those two, like x and y, they are independent, so they don't have any covariance, any co-movements. So again, the variance of x minus y is the variance of x plus the variance of y. And what's the variance of x? It's doable through a binomial distribution, which you all did like NPQ. I think that's a variance. If you want to find the standard deviation, is like the square root of NPQ, like you all did that in the last several homework when you are toasting 20 coins instead of 1,000 coins. So basically, again, you have the standard deviation of x minus y, you have the mu, you have the mean of x minus y, and you just plug in those two numbers in your z-score formula. You calculate your z-score and then compare that in the z-table.
Okay, thank you.
Victor, when I follow the steps that you just did, I do 0 minus 500 over like 7.07 or whatever. And that gives you like a z-score of like 70. Like, am I doing something wrong or?
You don't use 500, you use 0 minus
Zero.
50, right? Because they
Why
want to
is it
find
50?
the, because they're asking you the probability of the difference exceeding 50.
Oh, okay.
You're going to
Okay.
use your mu minus what the question asks, what you want to find out, and then divide it by the standard deviation. But I guess for this question, the probability would be kind of low, but I don't have any intuition of how low it is.
But even when I use 50, it still gives me a z-score of like 7, which is like a probability of basically 0, right? Like,
It could be. It could be.
okay.
I just had a quick question about doing the standard deviation. So when you're doing at least the variance for it, it's NPQ. So it'd be like what 1,000 times 0.5 times 0.5, which would just give you 250. So then if you're adding, because it's X and Y, because the first says 1,000, second says 1,000, you add the variances together to get 500, right? And then you can just square root that to get the standard deviation of X minus Y.
Yes.
Okay, thank you.
Yeah, so both the variance of x minus y or the variance of x plus y is the first two terms is the variance of x plus the variance of y. The difference is like you're gonna plus or minus the covariance of those two terms.
Okay, that makes sense. Thank you.
And then question 6 and question 7, right? I am looking at those two questions.
Question 6 is hard.
Yes. So I decided I talk about question 7 and leave question 6 for you guys. Those two questions, like their ideas are pretty much the same. But for question 6, you're gonna calculate some sub probability where you have to use the probability of a binomial distribution, like n choose k times p to the power of n times 1 minus p to the power of k minus n. You're gonna apply that probability mass function. So I talk about question 7. Okay, so for the first, like question 7, for the first container, you have 2 white balls, you have 7 black balls. The second container, you have 5 white balls, you have 6 black balls. So let's define event A, which is getting ahead, right? Because in the question ask what's the probability what is the probability of getting ahead given that a white ball was selected? So let's define event A as getting ahead and event B as a white ball is selected. So the question becomes what the probability of A given B? What's the probability of getting ahead given the white ball is selected? So I always do this approach, like, because it's easier to see. And we're gonna use the formula, like the probability of A given B is the probability of B given A times the probability of A divided by the probability of B. And we just need to calculate that 3 subset probability in order to get our final answer. First, what's the probability of B given A? which means what's the probability of white balls is selected, of white ball being selected, given I get a head in the coin toss, right? So what happened is I get a head in the coin toss means I'm gonna select the ball from the first container, which contains 2 white balls and 7 black balls. The probability of getting the white ball is just 2 divided by 9. There's 9 balls in total, and 2 of them are white. So the probability of B given A is just 2 divided by 9. What's the probability of A getting ahead? Straightforward, a half. So in the formula, the numerator is just 2 divided by 9 times a half. And what's more difficult is the denominator. What's the probability of white is selected, of event B? White is selected. And again, I'm gonna decompose it into 2 sub-probability. The probability of selecting a white ball is the probability of selecting a white ball in the first container plus the probability of selecting a white ball in the second container. So what's the probability of first choosing the first container? That means I have to get ahead in the coin toss. So you use 0.5 and then times 2 over 9. That's the first subset probability. And the second subset probability, 0.5 times 5 over 11. That 0.5 is the probability of getting a tail. That means you have to choose a white ball from the second container. And then after you choose to pick a ball in the second container, you have your probability of getting a white ball, which is just 5 divided by 11. So you just sum them up. And you sum them up and you kind of get the denominator. And that gives you the answer. So for all those kind of questions, it's for a lot of time, I think like 90% of the time, you cannot calculate the denominator by one equation, by one formula. Like in this case, the probability of B, which is the probability of selecting a white ball. You have to decompose that event by some sub-event. What is the probability of getting a white ball? First, I have to think about if I pick the ball from the first container and picking a white ball. That's the first scenario. And the second scenario is I'm picking a ball from the second container and getting a white ball. You have 2 like sub scenario, and you have to do that separately. So I guess that's a trick of solving those kind of conditional probability. And I think you have to use exactly the same idea in question 6.
Victor, I agree that we use the same idea for question 6, like with the base theorem and everything, but there's just one part of it that's tripping me out or messing me up. Sorry.
Yes.
So like we're looking for the probability that it's California given 4 guess French, right? So the first part of Bayes' theorem would be the probability that it's 4 French given that it's California. I don't know how to find that given the information in the problem.
I just answer a question, right? I won't check if your statement is correct or not. So what's your question? Like
My question is how to find the probability that it's 4 French given that it's a California, that 4 judges guess French given that it's a California one. So the opposite, the probability of B given A is what I'm looking for. I don't know how to find that.
Okay, so you're gonna use binomial distribution here, right? What does that mean is like 4 judges said incorrectly. So something you're gonna use is like 5 choose 4, right? So first what's the probability of 4 judges guessing incorrectly and 1 judge guessing correctly? It's 1 over 4 to the power of 4 times 3 over 4 to the power of 1. However, you don't know like which 4 out of 5 judges guessing incorrectly. So based on that, you have to multiply another term, which is 5 choose 4, because you can have any 4 judges guessing incorrectly. So what you're gonna apply, you have to use this kind of binomial probability mass function, and I just said it's 5 choose 4 times 1 over 4 to the 4th power times 3 over 4 to the 1st power. You're gonna use this kind of conclusion.
Okay, that makes sense. Thank you.
Yeah.
Wait, so that essentially will give you the B given A probability part of it, right?
Yeah, that gives you the probability of 4 judges guessing it's a French wine, given it is actually a Californian wine.
Also, I just have one quick question. When you're doing z-score, is it like the x variable minus mu over sigma, or is it mu minus x over sigma, or does it really matter?
Mm. Yeah, it's in a sense not really matter, but so you have to understand like in your z-score table, a plus z, for example, a plus 1.0 and a minus 1.0, you can find exactly the same answer in the z-score table, but like in this score table, I think they kind of have a hint like beyond z, like or something like between mu and z, right? They have a lot of different columns for you to locate the probability. I think it's the best way is to use mu divided by mu minus the frequency you want to find out divided by sigma, and then you're gonna locate like beyond z in the z-score table.
Okay, thank you. Thank you, Victor.
Sure. Yeah, I think I just like follow the order of all the questions, and just don't be afraid if you Like if you can't
Wait,
make
Victor,
sure. Yeah,
I
sorry.
actually have a question.
Yeah.
I actually have a question back on number 3. Sorry.
Yeah.
So when you do multiply them together, and I got 14.6 and 10.4%, and when you multiply them together, you get 1.5%. Since that 1.5% is equal to the 15 divided by 1,000, do we say that it's not independent?
No, we say it's independent. If that equality holds, we say it's independent because like the probability of A intersect B, if that just equals the probability of A times the probability of B, then we say like A and B are independent of each other.
Okay, I understand. Thank you.
Yeah, like a simple example, if you toss 2 coins, like what's the probability of getting 2 heads? 1/4. And what is the probability of getting a head in the first toss? It's 1/2. It's 1/2. The probability of getting a head in the second toss, it's also 1/2. It's also a half. And if you multiply a half by a half, which gives you exactly 1/4, and that means your 2 coin toss are independent of each other. So that could be a easy example to remind. So basically, whenever that equality holds, then you say the 2 events are independent. Other final question? Stop recording and